Hi guys, in this video I'll be explaining how we can derive the dimensionless form of the diffusivity equation for radial flow for a slightly compressible fluid. Okay, so this was actually part of a homework which I had, and so here we are provided with the radial flow diffusivity equation, and here we are given some conditions, and the question is to change the diffusivity equation to dimensionless form using these variables. Alright, so now let's go for our derivation. Now the diffusivity equation is, let me use white for this. Diffusivity equation is defined as 1 over r dou over dou r dou p over dou r is equal to phi mu ct over 0.000263 k dou p over dou t. Yeah, that's correct. Okay, and the dimensionless, so let me use a different color for this. How about use green? So the dimensionless groups are defined as follows. So first we have dimensionless radius, which is just equal to r over some rw, and this over here, I'll use green for this. So this rw is the wellbore radius. We then have dimensionless time, and this is equal to 0.000263 kt over phi mu c sub t r sub w squared. And hold up, so this term here is the wellbore radius, this term here is just the radius which we are interested in. Okay, this term here is time, and again this rw is actually wellbore radius again. And last but not least, we have our definition for dimensionless pressure, which is kh p sub I, which is p initial, over 141.2 bq mu. And again, this is just pressure, and this is initial pressure. Okay, so what is our objective? Our objective is to one, derive the dimensionless form of the above PDE, and 2, derive the dimensionless form of its conditions. So this will be both its initial and boundary conditions. Okay, now one final note. This PDE applies for constant rate production without skin and wellbore storage. Okay, because when we're talking about the PDE for diffusivity, when skin and wellbore storage is involved, it will be slightly different. And another important thing to note here is this word constant rate. So we also have another form of production, which would be constant pressure production, which has different definitions for the dimensionless groups. Okay, so let's move on to the solution. So the solution. So the most obvious way that we can do this, obviously, what is our objective again, is to remove the non-dimensionless terms. Okay, and to do that, we're going to start with the dimensionless radius. Alright, recall our diffusivity equation. 1 over r, dou over dou r dou p over dou r is equal to phi mu c sub t 0.0002637 k dou p over dou t. Alright, great. So let's have a look at where we have any dimension, any radius derivatives, derivatives that are involving the radius term. So if we have a look here, oh, for some reason I can't change my pen. Okay, here I can. Where do we have radius terms? We have them here and here. So these are both on the left hand side, which means that we will ignore this for now. Ignore for now. Okay, let's rewrite only the left hand side of the diffusivity equation. And this is what we'll get. Okay, so the first step that we need to do is that we need to recall the definition of dimensionless radius. So that would be Rd equals R over Rw. And this can be rewritten as R is equal to R sub D times R sub W. So now what we can do is we can rewrite the left hand side of the diffusivity equation in terms of this. So 1 over, I'm going to write that down a bit later. I'm going to write that down in red. And I'm also going to write all of this down in red. So here we have R sub D, R sub W. Here we have dou R sub D, R sub W. Here we have RD, RW. And we have dou RD, R sub W. We have a dou P up here. Okay, so here I've just substituted the definition of the dimensionless radius into the left hand side of the derivative. So now, how can we break this up? So the first thing to note is we'll break this up in groups. First, let's deal with the bracket in here. So I'll label this as 1. Then we'll deal with this, which I'll label as 2. Okay, let's deal with number 1. What do we have? We have R sub D, R sub W over dou R sub D, R sub W, and we have a dou P term up here. Okay, so how can we break this up? So we can actually just apply the chain rule to do this, and we know we can do this is because our objective here is to express in terms of dou P over, or let me use white for this, dou P over dou RD. So this is what we are interested in because we want the dimensionless form of the equation. So this is what we're interested in for now. Okay, so what does that mean? We can actually, so we can use the chain rule. That's a badly written rule, to write the following. We can write dou P over dou R sub D, R sub W. And remember, we want this in terms of dou P over dou RD. So let's just write that down on the right hand side. And next, we need to figure out what derivative multiplies by dou P over dou RD to give back dou P over dou RdW. Well, that would be simple. We have dou R sub D, R sub W in the denominator, and we have a dou RD to cancel off at the top. So using the chain rule, you can see that the left hand side and the right hand side agree, so this would cancel and this would cancel. Okay, so we want to leave the equation in terms of this, so we don't touch this. So don't touch. So we have to deal with this now, which I will label with, let's say, small I. Okay. So now let's deal with small I. We have here dou rd over dou r sub d r sub w. Now, how can we simplify this even further? At the moment, we do not know how to break this apart. But here is where we recall the definition of dimensionless radius. Rd is equal to r over r sub w. And using this definition, we can actually rewrite the top part, dou rd, as dou r over r sub w, and we can write this as dou r. Now, you can rewrite this as follows. And now we need to recall one more fact, which is that oh, can't change my color for some reason. Okay, there I can. R sub w is a constant. Alright, so that just means that we can just take it out of the derivative over here. Okay. So how can we write that? We can just rewrite this as 1 over r sub w, dou over dou r of r, and dou over dou r of r is just equal to 1, so ultimately this equals to r sub 1 over r sub w. Okay, now going back to the beginning, we can write dou p over dou r sub d r sub w. This is equal to 1 over r sub w dou p over dou rd. Okay, great. So let's go back up. We have just dealt with part 1 over here, and now let's deal with part 2. But first, let's summarize what we already have. So what we have now currently is we went from 1 over r dou over dou r. That's my bad. Let me rewrite this. We have 1 over r sub d r sub w dou over dou r sub d r sub w, and we have an rd rw in here, and we have a dou r sub d r sub w here, and we have a dou p in the top. So we went from here, and using what we have found in the from the breaking up the first part over here, we can rewrite this as 1 over r sub d r sub w dou over dou r sub d r sub w rd r sub d r sub w here, multiplied by 1 over r sub w multiplied by dou p over dou r sub d. Okay, and all of this, you'll see that this 1 over r sub w cancels out with this r sub w, and so we can just rewrite this in this form: 1 over r sub d r sub w dou r sub d r sub w r sub d dou p over dou r sub d. Okay, great. So now, how can we break up the second part, like we mentioned in the beginning? Alright, so using the logic from the previous, from part 1, we can actually rewrite dou over dou r sub d r sub w rd dou r sub d dou p. So we can actually rewrite this as 1 over, we can just take out the rw because r sub w because it's a constant, and we have a dou rd over here, and we can just rewrite this thing back. So you can actually rewrite this again, as I mentioned, using the logic from part capital I. But why? Why is this allowed? Why can we do this? To find out why, please watch the next video. Thank you.